Sometimes you want to know if there are correlations between two random variables. For example, is there a correlation between car age and the risk of being involved in an accident? Or is there a correlation between being good at language and being good at math? Or for example, is there a correlation between how much time you spend on mathematics and the grade you get in mathematics? The relations we want to study here are linear relations. That is, correlation can be described by straight lines. So for example, if you have time spent here on math, and then here you have point on the exam in math. Let's say our data are different students having different time and points. For example, if you have one student here, has spent this much time and has gotten this point on the exam, then perhaps another one here, another one here. So let's say you have gotten something like this. Does there seem to be a linear correlation between time spent on math and points on the exam? There seems to be some indication of it, because most of the points lie in a kind of a straight line. So you see, the more time you spend, the better points you get. Not very surprisingly, but it's not sure at all that it will be a straight line that will be the correlation. And there are some points here also that could question if it's linear correlation. But assuming that there is a linear correlation, that is, we can describe the correlation by a straight line, then how can you quantify this correlation? So if you have a set of data points here, how can you quantify the correlation between two random variables, in this case time and... So let's say you have gotten these data points, and you want to quantify the correlation between x and y. Perhaps this is your data point 1, corresponding to x1, y1 coordinates. And here is the coordinates of some point k, y, xk, yk. Let's say you have n of these points. If you take the mean of all the x coordinates here, that will correspond to some value on the x-axis. So here this line symbolizes the mean of all the x coordinates of the points. In the same way, you can take the mean of all the y coordinates. Then the mean of y coordinates will correspond to some value here on the y-axis. We see that these two lines divide up the coordinate system here in 4 parts, which we can call quadrant 1, quadrant 2, quadrant 3, and quadrant 4. In this case, we see that most points are situated in quadrants 1 and 3. And that's because the points lie on a straight sloped line. If instead the points would have lied here, then most of the points would be in quadrants 2 and 4. So we see that if there is some linear correlation between points, then we can find an indication of that by seeing that if most points lie in quadrant 1 and 3, or in quadrant 2 and 4, then that indicates that there should be some linear correlation between x and y. So if you can find some mathematical property that will indicate that if the most points are here or they lie here. And there is such a mathematical property, and that's this one here. So we take an arbitrary point with coordinates xk, yk. So for example this point. Then we take its x-coordinate minus the mean, and then we multiply that by the y-coordinate minus the y-mean. One sees that this distance here corresponds to xk minus x-mean, so this one. And this distance here corresponds to yk minus y-mean, so this one here. Now we see that if we have a point in the first quadrant, both of these will be positive, since the x-coordinate is to the right of the mean and the y-coordinate is above the y-mean. However, if you take a point in quadrant 2, this one will be negative and this one will be positive. And if you take a point in quadrant 3, both of them will be negative. And if you take a point here in quadrant 4, this will be negative and this will be positive. So if you look at the product here, in this quadrant the product will be positive. And in this quadrant the product will be negative. And this quadrant it will be positive since we multiply two negative numbers. And in this quadrant the product will be negative. So you see that if I have points in these two, this will be positive. And points in these two will be negative, this product. So we see that the sign of this product captures if the points are in quadrant 1 and 3 or in 2 and 4. So if you take the mean of this product for all points, if that mean is positive, that means that most of the points lie here. And if the mean of this product for all points is negative, that means that most of the points lie here. So calculating the mean of all those products corresponding to sum over all those products for all points, and then dividing by the total number of points. And this is almost what is called in mathematics the covariance of two random variables. So per definition the covariance is equal to this, but with the -1 here. So covariance is a measure of linear correlation for a dataset. And this covariance will be a number between -infinity and +infinity. The larger the number is, disregarding signs, so the larger the absolute value of this is, the larger the linear correlation is among the points. And if it's positive, we have that most of the points lie here, and if it's negative, most of the points lie here. However, there is a problem with covariance, because it's sensitive to what kind of data you have. For example, you could have a large covariance but still have small correlation. For example, if x and y has to do with stars and distances between stars, the involved numbers could be very large, even though the correlation could be small. So we could have a large covariance even though the linear correlation is small, just because the numbers involved are large. And similarly, you could have a large correlation, for example, if they have distance between atoms. So if, for example, x and y has to do with atoms and distances between atoms, then this could be small, even though the correlation is very large. So we need a property that's not sensitive for what kind of properties we're measuring. So it doesn't care if it's distances between atoms or distance between stars or whatever. And that measure is called the correlation coefficient, and is denoted by ρ, this Greek letter. And it's defined as the covariance divided by the product of the standard deviations of the two datasets. If you put in the expressions for these, it will become this expression. And here, since n-1 is involved both here, here and here, they will cancel. So this is the expression for the correlation coefficient. And the correlation coefficient is a number between -1 and 1. The larger the absolute value of the correlation coefficient, the higher the linear correlation. So 0 means no correlation, and 1 means maximum correlation. And positive means that the points lie in this direction, and negative correlation coefficient if majority of the points lie in this direction. So what would the correlation coefficient be for these datasets? In this case here we see that the points lie on a straight line, basically. So here the correlation coefficient will be close to +1. And in this figure it will be close to -1, since it also lie on a straight line, but going downwards. So here 1 and here -1. In this case also it lie kind of a straight line, but more spread out. So here about a half perhaps. And here it looks same as here, but they have a negative slope. So instead here you have -0.5 roughly. In this case there is no linear correlation at all, just a big cloud of points. So here it will be close to 0. In these two cases also there will be 0, because taking this case for example, you see no matter what x is, you always get the same y. And here, no matter what y is, we get the same x. So you see that x doesn't really care about what y is, and vice versa, y doesn't care about what x is. So there is no correlation between x and y here. So the linear correlation is 0, even though the points lie on straight lines. So for there to be correlation, there must be sloped straight lines, not horizontal or vertical. In this case, there is some correlation, but it's not linear. So this is more quadratic correlation. And if you calculate the correlation coefficient for this one, it will be close to 0. So even though there is correlation, it's not linear. So it's not captured by the correlation coefficient. So the linear correlation is 0. Let's take a concrete example of how to calculate the correlation coefficient. So first we need to calculate the means, x mean and y mean. And for the x mean, we have the x coordinates 2, 6 and 10. If we add those, divide by 3, we get 6. And similarly for the y mean, have 1, 5 and 6. So that will give us 12 divided by 3 equal to 4. Then using the formula for the correlation coefficient. So first take point number 1, and the x-coordinate for point number 1 is 2. Minus mean 6. And multiply y-coordinate for first one 1. Minus y-mean 4. And then we do the same for all points, all 3 points. Then we need to calculate these two. And since this is the same as here, so we just can take this one and this one and this one and square them and put it here. So this one squared becomes that one, then this one squared. And then we square that one. And same here, we take that one and square. And if you do this on calculator, this becomes 0.94. So it means that it's a very strong linear correlation between these 3 points. And that's because they lie almost on a straight line. And of course, if you have 2 points, they always lie on a straight line. So it's only the third that doesn't. But if you take a straight line corresponding to all 3, they still lie quite close to that one. So that's the next problem we want to face. If you have found the linear correlation, like here, how do you find a straight line that best describes this correlation? That is, the best describes these 3 points. And that's called a method of least squares.